Here we look at the effect of changing bases representations on operators, so how a change of basis affects an operator. And it's really pretty much the same thing. It's as we've seen before, except remember operators roughly we've said are in these Dirac notation are represented as matrices in some discrete sets anyway. And so let's look at a change of basis from phi to psi I. So I've got two orthonormal sets of basis sets. This psi I might be energies, and these might be momentums, for instance, basis sets. But they're complete orthonormal, and we can go from one to the other, as we've seen, by a unitary transformation. A unitary transformation, remember, the U inverse is the same as U dagger, complex, or the adjunct. And I can certainly make the transformation from the phi basis set to the psi basis set by injecting this operator, this identity operator, really summed over J. If you look at this. Here I've suppressed the summation. It gets a little tedious to always do the summation, but I'll use the Einstein summation convention that any repeated index is summed over all of its possible values. And so this is the injection of the completeness relationship, that this is just the identity operator. It's implicitly summed over J. And as we've seen, this phi Ji we could write as a matrix Uij. And again, implicitly summed over J here. A repeated index is summed over, and so the phi i's, this basis set can be expressed, the psi i's can be expressed in terms of the phi j's by this unitary, the elements of this unitary matrix, which I assume we've got, unless we've got a specific transformation. So now let's look to see what that does with a matrix. And so in the psi representation, we would get the matrix, or the operator components, by sandwiching it in between a psi I and a psi j. And then all I do is I insert these completeness operations, again summed over k, here, and in between psi I and a. And then here, do a sum over L. It's repeated index. And that's just an identity operator when summed over it by our completeness relation. And then look at the following. Well, in this case, I've got the matrix representation on the psi basis. I might call that A prime ij on the psi basis, but I've got a similar thing here. It's KL, but again I got a matrix for it, and that this without the prime I would call that on the phi basis, phi I basis. And then these two quantities, well, if you go back and look, these are just JL, and over here IK dagger. And as a result, we have essentially, in terms of matrices, that the same operator A, same physical quantity, has a different representation, but it's just this U dagger A U when A is represented on the phi basis. So these and since U is unitary, I could put a inverse here as well. Yeah? So either one of these. So in general matrices, you give me a unitary transformation to transform from one basis to another, and then any operator I sandwich in between that unitary operator and its inverse, or equivalently, since it's unitary, the inverse is equal to its adjoint. Then we could do either one of these. And these are, if you remember, in linear algebra, and this is like transforming matrices with what are usually called similarity transformations in the general linear algebra form anyway.